So the question we'll be looking at today is called search in a rotated sorted array. Well, when searching in an array, the most intuitive way is looping through every element in the array, but that will cause a runtime of big O of n being the number of the elements in the array. And when we think of searching in a sorted array, the first thing that comes into our mind should be binary search. We could also use binary search on this problem, but how do we apply it since the sorted array is rotated? Well, let's take a look at how many possibilities can we rotate a sorted array. So the first scenario is when the original head is moved onto the second half of the array. So if the original head is on the second half, what we could be sure of is that the first half, so between the current head and the current midpoint of the array, is still sorted. And we also know that the number at the current head is going to be less than or equal to the number at the middle point. And the second scenario is when we have the original head in the first half of the array. And similarly, what we could be sure of is that the second half of the array is still sorted. So from the midpoint to the tail of the array is still sorted. The number at the midpoint is going to be less than the number at tail. Moving forward, if we're currently looking at the first scenario, what we could do is to compare our target number with the midpoint and the head to see if it is in the first half, which is the sorted part of the array. If it is in the sorted part, we just further explore the first half, which is the sorted part of the array. If it is not, then we just move on to the second half of the array. Similarly, if we're looking at the second possibility of the sorted array, we then just compare our target to the midpoint again and see if our target is in the sorted part, which is the second part of the array. If it is in the sorted part, we then just further explore the sorted part. If it is not, we then just further explore the first part. And now let's see how we can implement it with code. So as usual, the first thing that we need to check is to check whether the given nonce is valid. So if not nonce or length nonce equals 0, we just return negative. And then we pick our usual start and end point. So usually the start point should start from 0 and end point is the end of the array. So length nonce minus 1. And these are just the indices of those numbers. Then we need to check while start is less than or equal to end. We get our midpoint, which is start plus end minus start divided by 2. This way it will avoid overflow issues if the array is too big. So let's check if the current mid is equal to our target. If it is, we just return mid. And then we need to check if it's not equal to mid. We'll need to check which possibility of rotated array it is, like we said before. So if the current start is less than or equal to the current mid, to the first scenario that we talked about, then we need to check if target is in this sorted section. If target is greater than or equal to nums start and target is less than nums mid, then we move our end to -1. Else, we just look at the other half, which means we move to the right of current mid. So we change our start point to mid +1. And else, which is our second scenario, we also need to check if our target is in the sorted part. So if target is greater than nums mid and target is less than or equal to nums end, then our start should be moved to mid +1. And if it is not the case, we move our end to mid -1. So after this while loop, if we still haven't found our target, that means the target is not in the array. We just return -1. Right? So that completes the code. And now let's take a look at the runtime and the space complexity. For the runtime, since we're doing a binary search, that means we're dividing up the whole array into halves and halves and halves until we find the target. So that means the runtime is going to be big O of log n. For the space complexity, since we're not using any other arrays to store anything, so the space complexity would just be big O of 1. It's a constant time. Alright, so that's it for today. Feel free to give this video a thumb up or comment down below, and I'll see you in the next one. Bye!